Now, the marginal value theorem is also related to optimal foraging theory, but there is kind of an assumption when it comes to optimal foraging theory that food is distributed evenly throughout an environment. That is an assumption that optimal foraging theory makes. And sometimes this is true. Sometimes foraging is in one place, right? Again, the best example is a grocery store. In nature, it doesn't really happen like that super often, right? Food is more often found in patches of food. And this is a pretty common term you'll see in this field. Food is referred to in terms of patches. You can think of bushes of berries, areas where worms live. But food is distributed patchily, not just uniform, right? Okay. Okay, so this marginal value piece from the marginal value theorem is the point at which the net energy gain from foraging at a patch becomes lower than the average gain of the surrounding area. Marginal value. So think of an area with several patches, lots of different patches. There's an average gain across those patches, right? One patch might be better than another, but the marginal value is the point at which the net energy gain, net energy, from foraging at a patch is lower than that average. Okay. So this theorem predicts that when a patch reaches its marginal value, that's when an animal moves on. An animal isn't just going to stay in one patch. No, yeah, sorry. The total, so the amount gained and the amount lost from foraging. Yeah. Good question. Right. So an animal is foraging in a patch. Doesn't necessarily mean it's going to stay there and eat everything in the patch before it moves on. That actually doesn't make a whole lot of sense. At first, maybe it seems intuitive. Well, yeah, you find a berry bush, eat all the berries. No, that's not what happens in nature. It's actually probably not what you would do either. Think about when you're berry picking. If you've ever been berry picking, if you've ever been apple picking, you don't take all the fruit off of a tree. You don't take all of the berries out of the bush. You say, okay, looks like I got most of them, or enough of them. Let's move on to the next patch, right? I actually think about this too in video games where you have to collect lots of resources. If you're familiar, there are certain games where basically it's based around the fact that you have to collect resources like wood and stone and different materials. Usually you don't mine everything, you don't chop everything to extinction, you don't clear cut everything, right? You say, all right, that's good enough, and I'm moving on. And I do wonder if people are kind of operating under a marginal value heuristic in that scenario. But that's a tangent. That's just a thought that I have when I'm playing games like that. Okay. But an important point, really, is that foraging at a patch depletes the supply at that patch, right? It brings it closer to its marginal value. So time spent in a patch foraging depends on two things. One, it depends on the resources in a patch and the time spent traveling between patches. Okay. So on this first little figure, you can kind of see what it's trying to show is that as you're foraging in a patch, the gains actually go down, right? If something's very abundant, it becomes easy to take a lot of resources from that patch, but then over time it becomes harder actually. It becomes less valuable because you're taking things out of it, right? So eventually your energy gain, food intake is going to kind of level off. So it makes sense to move on to a new patch. So here we're seeing it again in a kind of similar experiment to the one with the starlings. Here I think it's with a kind of chickadee. But same kind of idea, hide worms inside of little containers. And we already kind of talked about this, but the time in the patch is related to the travel time between patches as well. Okay. Okay, so how do animals know when to leave a patch? How do they decide? Decision making, right? Well, we know that they make these decisions in predictable ways, in optimal ways. We've seen this various amounts of times in lots of different studies. Animals generally follow an optimal foraging pattern, often follow the predictions of a marginal value theorem. Okay? So what that means is that animals must have a sense when resources in a patch are declining, right? They make a decision to move on to the next one. And again, it's not until it's all gone, right? Okay, so there was an experiment where there were 3 different environments. I can't remember what animal it was. It was a bird of some kind. Not super important. But there are 3 different environments. Okay? In these environments, they have logs with holes drilled into them where there could be worms. There's tape put over the holes. So the birds have to go in, move the tape to get the worm. Okay? Now in each of these different environments, so think different rooms, okay? Different rooms. Some of the logs are completely empty, and some of them are full. Okay. What that means, in this case, there's 24 holes in each log in all of the environments. Okay. But when it says full, at the top it means all 24 holes have worms in them. 12 would be half of the holes, right? And 6 would be a quarter of the holes. But they all have logs that are completely empty. And when it says full, it would mean 6 worms full, 12 worms full, 24 worms full. Okay? But there's still 24 holes. Does that make sense? It's kind of important to understand this part. Okay? All right. So really what you're seeing is this is a really rich environment, right? This is okay, and this is probably the worst one, right? Okay. What happens? All right, so that's what you're seeing there. It's the bird on this log. So they've learned, they know how to peel the tape off and all that. But what do we find? Okay. All right. So in the full patches, these are the patches that have 24 rooms. You know, kind of predictable. Okay, they open, they don't even open all of them, but they open 22, generally, around there, right? When we look at the empty patches, these are the interesting ones. So again, these are different environments. Full, half full, quarter full. They realize very quickly, in the full environment, the ones that are empty, there's no point taking time to open the holes. Because they have an idea that it's a very resource-rich environment, right? Well, this one has none. I need to move on to a good one. Because they figured out that in general, most, or some of the logs at least, will have a lot of food in them. But you don't see this pattern as much in the half-full environment and in the quarter-full environment. We'll actually try to open more. Okay, you can see that visualized again here. Might make it a bit clearer. Again, these are the empty patches, so there's no food. There's no food in them. Think of the full, half full, quarter full as the environments that they're in. The arrows are what marginal value theorem would predict. Okay, that's where the black arrows are. And then the bars are the actual data. And you can see that the animal's behavior actually lines up pretty well with what this theorem would predict. So they have an idea of how rich the environment is with food. They can tell what the average state is. Questions about that? Okay. Right. Good. I'm glad I put this here. This is the key point here. Animals have knowledge about the general patch payoff within a habitat. That's the thought. Okay. All right. So how do animals know what the payoffs are for different patches? How do they know that? They can't just enter an environment and know, ah yes, this is rich, filled with food, right? Especially if the food's kind of hidden. If it's very visible, you could use vision, right? Perhaps some other senses as well. But let's say things are kind of hidden, obstructed from the senses. You can't just enter an environment and intrinsically know how much food is there. So how do animals know what the payoffs are for different patches? Well, they use something known as sampling. Okay? really what it is it's visiting patches. Right? Gather information about the payoffs. Visit several patches in an area, helps you decide when and where to move. Of course, memory might come into play with this as well, right? Remembering the quality of the different patches and kind of getting an average of the patch payoff. Helps decide when and where to move. Helps decide when and where to move. Right. So you can't, of course, spend all your time sampling, right? You need to spend some time foraging, because that's the whole point. So there is a balance, right? That's based on the difference between rich and poor quality patches. So as the difference in patch quality increases, animals will spend less time sampling and more time foraging in the most profitable patch. So there's a trade-off. You can't spend all your time sampling. And when there's a difference there in patch quality, they'll spend less time sampling and more time foraging. Okay. All right. Let's now talk about decisions as a group. Okay. Not necessarily talking about cooperation here. This isn't about helping behavior. This is making decisions as a group. Okay. All right. When it comes to collective decision-making, decisions as a group, there's this idea of ideal free distribution. So sometimes animals don't forage alone, right? They forage in a flock, they forage in a large group. But the payoff of resources in a rich patch is going to be lower. There's a lot of animals foraging there, right? Makes sense. So the number of animals aggregating in a food patch is going to be proportional to the amount of resources available at that patch. Okay. So really what it comes down to, they're all actual individual decisions. They're not, again, it's not cooperation, but it affects the pattern of behavior of the group. So if you're in a large flock of animals, and you are one of those animals, a better strategy isn't to all just lump up in the same patch. A better strategy is to actually distribute yourself across patches. Okay. What does that mean? Okay. So some experimenters did experiment, as they do. What you're looking at is a fish tank, right? So these fish will commonly school together, they forage together. They wanted to see how these animals distribute themselves across different food patches. So they had different rates of food being released, okay, at two ends of the aquarium. 30 insects per minute at one side and 6 insects per minute at the other side. So that's a 5-to-1 food distribution. And what you end up seeing is that the group actually splits itself up as well. So this is what is known as ideal free distribution. And people do this too. People do this all the time. Here's an example. Probably thought about this before. 2 long lines for different kinds of coffee. You'll make a decision on which line to go in based on many different factors, right? Which one do you like better? So which one's more high value to you? There's a lot of different factors. But let's just say even the coffee is exactly the same place. You'll split yourself, you'll go in the shorter line, right? Of course you will. So people do this all the time. Ideal free distribution. Now if you have a really good coffee shop and a really crappy one, you might wait a little longer, right? You can think of that like right? One has higher quality, they split themselves up proportionally, right? But people do it too, they split themselves up proportionally. Of course, again, there's going to be individual differences. There's people, there's marketing, there's all sorts of differences, but it's a neat kind of little thought experiment. Okay. All right. So collective decision making is kind of this really neat phenomenon when we watch animals moving as a group. And in particular, one I really like is something known as murmuration. So this is a bunch of many starlings flying together. It'll load. Just give that a second. But you've probably seen these before, right? When you see big groups of birds flying in the sky, if you get close enough to them, they make this really mesmerizing sound, actually. And it is really beautiful, right? And you might wonder, how do the birds know to fly like that, right? How do they know to fly in a group? And I think the computer is completely frozen. Awesome. Okay. Well, we're almost done the first half, so I think what we'll do is we'll just take our break here while I troubleshoot this. So we'll talk again in about 15 minutes, okay? I'll try to figure this out.